Hello, everyone. Welcome to our little talk about how having source access to DOTS packages has helped V-Rising achieve the success it enjoys. We're going to look at 2 or 3 case studies and how source access to entities is instrumental for V-Rising. With me, I've got a special guest today, Rasmus from Stunlock Studios. Rasmus, why don't you just introduce yourself?
Thank you, Sebastian. Hello, my name is Rasmus, and I have been working here at Stunlock Studios since we created a company back in 2010. I am working as a software engineer, but I have a past as a technical artist. On this game, I've mostly been working on trying to make a game in ECS and trying to utilize DOTS the best we can, as well as a lot of optimization work and general backend stuff.
And I'm Sebastian from Unity. I work as an engineer in a little-known part of the organization called Emerging Technologies, where I spend my time solving Unity's problems in customer projects. And occasionally, like in this case, I also hack on those projects myself. If you have a particularly slow Unity project yourself, either slow at runtime or slow in the editor, when you're editing, you're always welcome to reach out to me on Twitter. Now, Rasmus, into the action. Let's get us started with V-Rising.
Thank you, Sebastian. All right, V-Rising is an open world vampire survival game. You can play this solo, or you can play this with your friends, but you can play it on servers with up to 50 concurrent players. And making this game, there was a lot of challenges ahead of us. We've never made a game like this, so the world was going to be massive compared to what we've done before. It was going to feel live, so there was a lot of stuff going to happen. On the client, we needed to be able to stream in the world as the player moved around. And on the server, we needed to save the game, and we wanted to do it fast enough, to not make spikes. And to us, DOTS looks very promising because it seemed like the challenges we had seemed to align very good with what DOTS was trying to solve. So we started using DOTS as soon as it came out, just experimenting with it, and we decided to use it already in version Entity 0.2. So we are very early adopters. And having this big game ahead of us and using an experimental package, having source access was very important. Just being able to fix a bug or improve something, or just look under the hood and see how something works. Because I've spent many hours in our previous games, just experimenting with Unity, just trying to figure out how it worked under the hood. But now we could finally see. And to be honest, if we didn't have source access, we would probably not having had the courage to make the game in DOTS, and we would probably not have made it in Unity unless we scale it down quite a lot. Okay, so the first case study we're looking into here is worst performance over time. And this is something we noticed as soon as we had a game ready to play, that seemingly V-Rising is a server-based game. So we have servers that are up for many hours or even days. So after a few hours, we noticed the performance was significantly worse than a freshly started server. And just looking at the profiler, there was nothing in particular that stood out. It was just all across the board, it was slower. Actually, just checking if the system was supposed to run had a significant cost compared to when we first started up the server. And into this version we have, since we now have source access, we can look into how it works. We're using entities 0.17. And when a system is deciding if it should run or not, it does so either by having been tagged by always update system, and that is very fast. It's just a boot check, so that's not slow. The other way is checking if do we have any entities that we are going to process, because if we don't have any entities, then why bother running the system? And it does so by checking the required queries and checking for the matching archetype list. And as soon as it finds an archetype that have any entities, it returns yes, should run. And since this was slow, we decided to look into the data. Like, how many archetypes are we actually talking about in this game? But before we look at data, let me just briefly explain what an archetype is. So in the ECS manual, it says an archetype is a unique identifier for all the entities in the world that have the same unique combination of component types, which means an entity always belongs to an archetype. And if we remove or add a component from it, it will change into a new archetype. And if that archetype doesn't exist, because that's a new unique set of components, then a new archetype will be created, and the entity will belong to that one. So again, looking at the data, this is data I pulled from a server just a few days ago. And here we can see in the beginning when starting up the server, we had 14,000 archetypes. And after 24 hours, we were up to 30,000. And our first approach was not dive into the package and try to modify it. We tried to solve this from our side. And we did that by trying to make fewer archetypes over time, by adding or removing components less pretty much. And we did reduce a lot. This increase was much bigger when we first noticed this. But there are archetypes that are going to happen, especially like how we have structured our game. There are some archetypes we can't really, they have to be created. For example, when we are instantiating a prefab, many times it comes with a spawn tag component on it. And once the spawn systems have processed it, then we will remove that spawn tag component. And when we destroy, we put on a destroy tag. And when we disable stuff, we put on a disable component. So just from that first initial archetype, we now have 4. So it's natural for archetypes to grow. And as we add more content to the game, we will also add more components and new archetypes will be created. And if we remember the code, like it was looking through the archetypes, trying to find any entities alive. So if that's slow, that must means we're going through a lot of empty archetypes, right? So if we then start to track how many active archetypes are there, how many archetypes actually have any entities, then we can see from the beginning it's 3,000, and that was stable all over the 24 hours period. So by knowing this, we decided to, okay, let's see if we can actually make a change in the package. So that's what we did. We are keeping on each query, instead of keeping a list of all the archetypes, we still do that though. We are also keeping a list of active archetypes. So that means the check if a system should run or not, it's almost instant because it always finds one very early. But there is maintenance of keeping an archetype active or deactive, because we have to, when activating an archetype, that has to be fast, because we want to be able to query that archetype right away. So that's instantaneously, and that's pretty fast as well, because we're adding it in the end of all the active archetype list. But removing and deactivating an archetype is slower, because we have to find it in the list of active archetypes. But that's not something we really have to do right away either, because the problem we are trying to solve is worse performance over time. So if we remove it a few frames later, or even a minute later, that's not a problem. So instead, we are doing it like we're checking an archetype maybe every frame, and are you going to deactivate? Then we do it. And this is, why we had to do this was because we are such early adopters and we are using an experimental package. It's already been fixed in the entities version 0.50. Then it's already much faster. It is using a cache. So once we upgrade, we have to see like, is our change going to make it, or don't bother maybe. All right. So that's better. Our performance got maybe 10% better, and checking if system should run didn't get worse. But there was still something that we were worried about, and the performance did get worse over time still. And this was something that we were a little worried about, could become a problem. But before I talk about that, let me just briefly explain another concept in ECS, which is archetype chunks. So archetype chunks is where we store the entities and their components. So an archetype doesn't have a list of all the active archetypes, active entities in it. It has a list of chunks, and then the chunks have a list of the entities in it. A chunk is always 16 kilobyte big. And how many entities can fit in a chunk depends on how big the archetype or entity is. And that depends on how many components and how big they are. So if an entity or an archetype is 1 kilobyte big, because that's how much the component takes up, then you can only fit 16 entities in one chunk. And actually, when we are iterating over chunks in a system, and this is one reason ECS is so fast, we are iterating over components the system want to use. And when we're iterating over those components, we're actually iterating on these chunks. And inside the chunks, we're iterating over an array of that component. So in the case, if we fit 16 entities in one chunk, we're actually iterating over an array of 16 elements, which is quite few. You usually want to aim for quite a lot more in a chunk by using less components. But why it's so fast, it is good to iterate over arrays. And why it's so fast is because we're accessing memory linearly. which means the CPU can kind of predict where are we going to access memory next. So that's much faster memory access. Another reason is that there are opportunities to optimize this with SIMD for working memories. All right, so by knowing what an archetype chunk is, what we were a little bit worried about was something called chunk fragmentation. And that is, instead of an archetype have a list of a lot of chunks which are full of entities, it has a list of chunks with partially full, or the entities are spread out thin in many chunks. And it is good to, it's better to iterate one big array than many small ones, because every time you access a new array, you are going to get a cache miss. You're not accessing linearly anymore. So here's an example of chunk fragmentation happening. So when we're adding entities to an archetype, we are filling a chunk. And when that's full, we're filling another chunk. So in this case, we have 2 chunks in this archetype with 6 entities in each. And when we start to remove entities, we are removing entities from the chunk they belong to. So we can see they are starting to get partially full. And imagine like having a chunk over time that has 100, an archetype that has 100 of these chunks, and they all look like this. It would be much better, of course, to have fewer chunks that are full. Another reason fragmentation can happen is if you are using you are adding or removing components on the chunk instead of the entity. And it's super useful to be able to do this because it's usually much faster than doing it on entity level. And if you're removing a component or adding a component that has no size, that component doesn't store any data inside the chunk. And we can just convert that chunk into the new archetype. But if that chunk is not full, we are converting a partially full chunk into the new archetype. We're not merging it with any existing chunks. So this is another source of fragmentation. So what we decided to do was implement a chunk defragger. So every frame, it analyzes an archetype, and it checks if there are any chunks that, any archetypes, any chunks, if it's using the ideal amount of chunks. And if it's not, it merges them. And this is quite straightforward, unless you're using shared component data. And shared components is another concept in ECS where we can group entities together. So a shared component guarantees that entities in the same chunk always have the shared component data. And this makes analyzing a little bit harder, because then we have to consider that chunks can only merge with each other if they have the same shared component data. So that's a trickier analysis. And we had particularly hard archetype on our client side where we're using render meshes. That's how we render stuff in ECS. And a render mesh has data, material, and mesh. So it means that it is grouping entities with the same render pretty much, and it's very fast to render. However, we had a lot of entities that belong to a certain archetype with this component, and they all had slightly different shared component data. So that archetype was quite slow for us to analyze. And I imagine that's a common problem if you're trying to implement something like this yourselves. Implementing this chunk defragger was actually, we were surprised at how much better it got. It was like maybe in the 30 or 50% increase in performance. So we had big problems with chunk fragmentation. Okay, so adding these 2 changes made our performance not get worse, it stayed the same. The first change, we had to modify the package. The second change, we didn't have to modify the package. All it took was using the internal functions. And you can do that by using an assembly definition reference. And if you can use that instead of modifying, I would recommend that, because it is a little bit tedious having modification in the package, because you might want to upgrade and then you have to re-implement your modifications. So these changes, yeah, it made performance not worse over time, except, of course, if there is more content, more players alive, more castles being built, but then at least it scales with content instead of just deteriorating over time. All right, that's it for me. Thank you. Over to you, Sebastian.
Thank you, Rasmus. Now we're going to look at a second case study, or a third, depending on how you count, where changing just some internals of Unity physics has yielded a major speed up for re-rising, particularly the server. I think this one is particularly interesting to look at because the 2 two examples that Rasmus gave you, they were really a little bit game agnostic, if you think about them. Chunk fragmentation, well, that can happen in any game. The same for the caching of the archetypes. That could happen in any game. You can make an argument that can be useful for any game. Where in this case, the third example that I'm going to give you shows more how specific knowledge of your game can allow you to gain much better performance than what is possible out of the box. Why is this interesting? Well, this specific game knowledge is knowledge that Unity doesn't have, that we cannot have, and that only you can bring to the table because it's specific to your game. Unity's technology supports all different kinds of experiences, even if we just look at like the few examples that we've built with dots and shown over the last few years, like Megacity or Shooter or a strategy game. These are very different kinds of games, and still we need to support them all equally well. So the choices we make need to support all of them. With entities and the associated packages, our thought has always been that it must provide a reasonable starting point, a good default. We can't possibly do everything optimally all of the time because we just don't know the particular constraints for your game. We don't know what optimally means for your game, what data you have, how you're using it. But we can give you a good starting point. And then when you need to get just a little bit more performance, you can change the code to your needs because entities ships as a package that you can modify for your project. The motto then must be understand your constraints by measuring, then customize Unity's offerings with precision. To set the stage for our third problem, we need to learn a little bit about how vRising works internally. One of the core entities features that vRising is using is streaming. The world is divided into many small sectors, and each sector is streamed in and out depending on the player location. There are also some persistent entities that are not tied to sectors, but the majority of the entities in the game go in and out of existence as needed. This allows the game to represent a big open world without overloading the system. You can see some of the sectors here in this editor view. Each of these little red boxes is actually a sector. Now there's a catch to this. vRising is a multiplayer game, and naturally there's a server. That server may have 50 players strolling around, sucking blood, doing things apt for a vampire as one does. For the server, it's actually more beneficial to keep all of the sectors loaded at all time because it's likely that players are going to be moving in and out of them frequently. And instead, we just disable the parts of the world where nobody's currently doing any vampire business so that they aren't simulated at all. But then there's also the worst case scenario. Imagine you and your 49 vampire siblings decide to kick back for a relaxing evening of vRising, and because you're siblings and never get along with each other, you each have your own separate vampire castle built in a separate part of the map, sleeping in your own separate coffins and partaking classic survival game activities such as clicking trees to collect wood, which incidentally is a physics interaction in different parts of the world. In short, you're all spread out across the entire map, and the server has to keep all the data resident in the simulation. It cannot disable anything. This means that the number of entities loaded on a server is potentially way higher than what you see on a client. Every tree, every rock, every fence is an entity after all. Just to give you a slight idea of the sort of scale that we're looking at, here's what you see in the entity inspector in a smaller test case. That's not actually the full size of the dedicated server. It's about 168,000 entities. Keep in mind that this is actually an old version of the inspector, since vRising is still using an old version of entities. As said, they're early adopters. I should note that large numbers of entities are not necessarily a problem if you don't touch them. But in this case, as you're going to see, we do touch them. And we touch them every frame, which is the problem in the end. To understand why that's happening, I will have to tell you a little bit more about how vRising's gameplay code uses physics. So vRising uses Unity Physics, which is a physics package that we ship with entities. Some of the physics systems run on both the client and the server, others are client or server specific. On the client, there's a lot of dynamic simulation. When you chop a tree, it falls, it hits the ground, maybe bounces around a little bit, it rolls. This kind of dynamic physics is arguably very important for immersion, but in this kind of game, it's actually irrelevant to the gameplay. Nobody's getting crushed by falling trees. For gameplay purposes, actually, vRising is only using static physics. In concrete terms, that means that every entity that is relevant to the simulation, the actual gameplay, trees, stones, creatures, players, buildings, they all have a physics collider attached to it. That's what you can see here in pink. When you cast a spell or swing your weapon wildly, these colliders are used to determine what you hit. And that's not an actual simulation of things moving on the server, but many, many ray casts, fear casts, collider casts, all the different casts that you can imagine. They drive a large part of the gameplay. And that's why static physics needs to be present on the server. To give you an idea of what the number of colliders we're looking at in this worst case scenario where we're all spread across the map actually looks like, take a look here. So this is a test with 50 clients spread out across the world, your siblings, that's the story. You're all in different spots, and we're looking at roughly 53,000 colliders. They're all part of the simulation. We can't disable them because every one of them has a player near to them. It's actually likely somewhat worse for a real server than this test case here. And one of the defining features of Unity physics then is that it's stateless, meaning that it doesn't keep much, if any, state outside of these physics buddies and colliders that participate in the simulation from frame to frame. There is no internal physics state that exists between frames. Instead, we will rebuild whatever acceleration structure is needed from scratch every frame of the simulation. This was a conscious design choice when the system was built. And once you reach a certain size of the simulation, you have to work with that constraint. In V-Rising's case, the server hits this performance limit. Here's actually what happens every physics frame, illustrated by an example where I just took 55,000 colliders and looked at the profiler. There's two boxes here, two blue boxes. We first collect all colliders on entities. That's the left box, blue box, because as said, stateless, we don't keep the collection of the colliders. We have to collect them all of the time. And then on the right, we build an acceleration structure from these colliders to do all of our casts very quickly. That's what we see on the right-hand side. That's where we build the bounding volume hierarchy. That's the right blue box. If you've actually caught Unity's live stream with Rasmus and his friends from Stunlock a few months ago, you already know that V-Rising has heavily customized and optimized the collider collection stage of this process. That's the left blue box. The game is saving a lot of time by keeping track of changes to colliders manually, so we do not have to collect them anew every frame, but can instead rely on a cheaper update process. Amazingly, this change did not actually require many changes to the Unity physics package at all. It just plays nicely with it. Which brings us to the second part of this process, the right blue box, which I've divided up further here, building the bounding volume hierarchy every frame. Unity physics has been carefully engineered to allow this crucial process to happen in parallel and asynchronously, usually. This means that if your machine has, say, 16 decently performant cores, Unity physics will use all of them to breeze through the bounding volume hierarchy construction by using a few parallel jobs. First, it takes some time to do some setup, and then it spreads out and goes parallel. It still takes some time, but this time doesn't completely dominate the frame. So at this point, it's worth remembering what running a parallel job actually looks like on a server. It looks kind of like this. You can see that there's not a lot happening because it's all happening on the main thread. On the server, we don't want to use all of the job threads. A dedicated server, in all likelihood, should not use 16 cores. It should ideally not even use one core fully. The goal is generally to keep these servers running for cheap. And the more server processes we can run on a single machine, the better it is. Long story short, building a bounding volume hierarchy for 53,000 physics colliders every frame is not sustainable on a server where you're running on a single frame because it's going to cost you 10 milliseconds per physics frame. So what do we do about this? Clearly, we cannot rebuild this bounding volume hierarchy every frame. We just can't afford it. But what to do instead? We could make the entire Unity physics package stateful. And that immediately suggests this siren song of incrementally updating bounding volume hierarchies with carefully selected tree rotations to keep itself balanced. But while that sounds error-prone to implement, sounds like actual work. I don't like work, and we only have a few days to do this. And I'm not convinced this is really necessary. Can we get away with something that is simpler, that ideally doesn't involve the word tree rotations? What's the smallest change that we can get away to solve this? So the curious and observant among you may have already started to ask themselves, what exactly are those 53,000 colliders anyway? And I think that's exactly what we should be looking at in the same way that Rasmus said, let's look at how many of these archetypes are actually active. Look at the actual data that you have in your actual game. When you're working on your game, you have the luxury of only having the constraints of your specific game and not all the baggage that the authors of the package carried to build something that works for many, many, many different games. So it's in your best interest to get to know your constraints intimately. In the particular case of V-Rising, I was lucky enough that Stunlock's earlier work already tracked which colliders are created, destroyed, and move around. That's the optimization that they had already made to avoid the costly first step of Unity physics. Go watch the live stream. This is the part about collecting all colliders every frame, so naturally they already had to track that. This sounds exactly like the kind of data that we should try to understand here. Like, what is created? What is destroyed? What moves around? What are these colliders? Thankfully, a magic tool was bestowed upon us developers to look at this data easily and confidently. And this tool is, just writing it all out to a log file and using printf. It sounds dirty, but I think it's the right thing to do. The easiest solution really is just write some lines of code and make those lines write out something to your log file with a prefix that you can easily extract. In this case, I chose to write our data in a comma-separated values format every frame. The data I collected is how many entities have moved around, how many were destroyed, how many were added. And then we split that data further up by archetype so we can see which entities actually were affected, what archetypes were involved. Archetypes will then allow us to reason about what kinds of entities are they. Is this a player character? Is this a projectile? At this point, I have to formally apologize before we move on. I have to apologize for what you're about to witness on the next slide. I'm especially sorry to you if you're part of Unity's branding department and we're probably already furious at my rebellious misuse of our slideshow templates. Again, I'm very sorry. I don't do it on purpose. The following does in no way or form reflect Unity's branding choices and is entirely on me. It's a spreadsheet on a slide. It's ugly, I know. But that's kind of the point. Bear with me. Let me explain a little. So what you see here is this. First, there's how many times an entity with an archetype was updated, added, or destroyed. Updated means that the entity moved around in space. And second, you can see what the archetype consists of, the list of components. The specific aren't that interesting here. This table is sorted by how many updated entities there are per archetype. Let me make 3 quick callouts. First, the number of colliders that are actually moving is surprisingly small. It's about 3.5% of all the colliders we have in total. That's the stuff that actually causes the bounding volume hierarchy to have to be rebuilt every frame. Second, the vast majority of colliders never moves. That block down here. These unmoving colliders are not removed or re-added frequently either. That's rare. And third, almost all colliders come from very few archetypes. They are highly uniform. Let's return to why I'm showing you this ugly duckling. Yes, the findings are important, but more important is that you see that I did not build a beautiful data pipeline. I did not write a profiler plugin. I did not even use a structured logger. Instead, I took 5 minutes to hack together a printf statement, filtered a log with search and replace in Notepad++, and then dumped it into Google Sheets. And you have my permission to do this too, because you have to get to know the constraints of your game, the actual data. With that said, the first message here is, go forth and measure. This is important. This is the advantage, the leg up that you have compared to the engine developers on Unity's side. Use your constraints, understand them. Now, back to the data. I learned from the data the astonishing fact that V-Rising has trees and rocks and fences. Nobody could have guessed this from just playing the game or looking at a screenshot. But joking aside, now we actually have the data. We know that 96% of the colliders are completely unmoving because they are trees, they are rocks, they are fences, they are barrels. And the moving colliders that make up the rest, well, it's animals, creatures, enemies, projectiles. What did I do with this data? Well, I decided not to write an incremental bounding volume hierarchy. The solution isn't actually all that interesting. I changed like 30 lines of code in Unity physics to have a separate bounding volume hierarchy for things that really never move. And then every once in a while, we update that thing. We only recompute it when something new streams in, which on the server is never. And when a tree is destroyed, we don't even update the hierarchy. We just invalidate a reference because we know that within like 30 seconds, we're going to get a new tree there because trees regrow. The effect, we save multiple milliseconds per frame at the cost of making some case for collider casts marginally slower. So what's the takeaway? Unity systems strive to be a good default choice. Customize them when you need to. You have my permission to embed and modify packages and make them your own at your own responsibility. Your games has constraints that are specific to it. Measure, look at the data, figure out what your constraints are and where you can take shortcuts. With that said, thank you so much to Rasmus from Stunlock and the rest of the team for collaborating with Unity on this talk. And thank you for listening.